Hello everyone. In this session, I am going to explain about the continuity equation. The continuity equation for the fluid flow in the fluid mechanics I am going to explain here. The continuity equation is the equation based on the principle of conservation of mass, and that equation can be used for the one-dimensional flow and the three-dimensional flow. In this session, I am going to explain the continuity equation for the one-dimensional flow. And in the further session, I am going to explain the continuity equation for three-dimensional flow also. Moving to next, here, what is the continuity equation? Will take first definition. The equation based on the concept of law of conservation of mass is called the continuity equation. The law of conservation of mass means it is a mass is neither created nor destroyed, and it will be same across the section of the flow. That is the law of conservation of mass. Here, that law of conservation of mass can be explained as the flow of fluid in a continuous flow across a section is always a constant. Across a section, the flow of the fluid in a continuous flow is always constant. Here, consider an enlarging section. Consider an enlarging section. In a fluid flow of fluid density ρ, consider two sections 1 and 2 as shown in figure. Let the sectional properties be as under. Here, the two sections what we are considered for the enlarging section that will take first, and the same will be applied for the converging section also. Here, this is the converging section. At the two sections 1 and 2 we are going to take the same equation. What we are going to develop for the this enlarging section is same for that converging section also. I will take that is properties. A1 and A2 are the cross-sectional areas at section 1 V1 and V2 average flow velocity at section 1 and 2 ρ1 and ρ2 fluid density at section 1 and section 2 respectively. Then dt is the time taken for the fluid to cover the distance dx. The distance between the section 1 and section 2 is the dx. To cover that distance, the time taken is the dt. Then the mass of fluid flowing across the section 1 is given by, that mass is given as m1 equal to density at section 1 multiplied with the volume of fluid that has crossed section 1. Okay, here density at section 1 is taken as the ρ1. The volume of fluid that has crossed the section 1 is given as cross sectional area multiplied with the distance that has crossed. Similarly, the mass of the fluid flowing across the section 2 is given by m2 equal to density at section 2 multiplied with the volume of fluid that has crossed the section 2. Then density at section 2 is taken as the ρ2 multiplied with the cross sectional area A2 and dx, the distance has crossed by that fluid. Then next we'll take that is the mass of the fluid we have taken at section 1 and 2. Now we'll take the mass rate of fluid flowing across the section 1 is given by the mass rate of the fluid flowing will take. That mass rate of the fluid is given as the m1 by dt. That is mass by time. That is the mass rate of the fluid flow. That is equal to density at section 1 multiplied with the volume of fluid that has crossed the section 1 by time dt. That is written as mass density ρ1 and cross sectional area A1, and that will multiplied with the dx, that is the volume that has crossed the section 1 by time. Now we'll take this ρ1 and A1 as it is, and dx by dt term whatever is there, it is the distance per unit time or a displacement per unit time, and the displacement per unit time is the velocity, and that is at cross section 1 is taken as the v1. and this will become say rho 1 A1 V1, and that will take as a equation 1. Similarly, mass rate of fluid flowing across section 2 is given by m2 by dt. Therefore, density at section 2 multiplied with the volume of the fluid that has crossed section 2 by time dt. Then that we can write density at section 2 rho 2 multiplied with the cross sectional area A2 multiplied with the dx to get the volume of this one, and per time we are going to take dt. And the rho 2 A2 as it is will write, and dx by dt term is the displacement per unit time at section 2 that is the velocity at section 2 V2. Then this becomes rho 2 A2 V2, and that is taken as the equation 2. Then now, from law of conservation of mass can neither be created nor destroyed. Hence, from equations 1 and 2, we get these equations we can equate because of the mass can neither be created nor destroyed. Therefore, mass flow across any section, if you take, those are equal. Then those written as rho 1 A1 V1 is equal to rho 2 A2 V2. Then here, if the density of the fluid is same on both the sections and the flow is incompressible, if the fluid flow is incompressible, then density will remains constant at sections. If the density remains constant, then we can write the rho 1 equal to rho 2. Then in this equation rho 1 equal to rho 2, if you take, those will be get cancels. Then the above equation reduces to A1 V1 equal to A2 V2. And this equation is the one-dimensional continuity equation for steady state incompressible fluid or steady state incompressible fluid. The above equation is the continuity equation for one-dimensional steady state incompressible fluid flow. And in the next session, I am going to explain about the three-dimensional continuity equation derivation. Thanks for watching. If you like, share, subscribe, and comment.